Okay, Algebra 2, we move into section 13.3 and we learn something that seems pretty darn scary at first, and that is this concept right here of radian measure. Now, when we talk about radians, what we're really dealing with, and I'll go ahead and give you the definition of it right here, a radian is a unit for measuring angles. So in that regard, the only unit that we know so far for measuring angles, everybody, is degrees. So this is kind of like talking about feet versus something in the metric system like maybe meters. Now, feet and meters are both two different units that do the same thing. They both measure the distance or the length of something, but they're just two different systems in which to measure it. Well, radians and degrees kind of exist in that same space. They're both measuring angles. That's what's really important, but this is just a new way of measuring it and talking about an angle measure other than degrees. And the nice thing about radians is that it fits pretty well with what we started talking about in section 13.2 on the unit circle. So this big idea, we'll write this again on a subsequent slide here in just a moment, is the main concept right here, guys, that one complete circle, which by the way, of course, you all remember is equal to 360 degrees, that amount is equal to 2 pi radians. So that's a weird thing, guys. Radians is almost always, now, not 100% of the time, but it is usually measured in terms of pi, and that's a little bit weird. So one complete circle, guys, from here all the way back around to where we started is equal to an amount called 2 pi radians. Just like it was equal to 360 degrees, it's 2 pi radians. Now, I don't want to spend too much time on this because I know that not that many people are interested in it, but the logical question for you guys to be asking right now is why? Why do we need to learn a second system? Why do we need both feet and meters? And there's not really a great answer for that. It would be cool if the world could just agree on one, but we work in different ways there sometimes. So a quick explanation. The reason why radians exist and why they're still used, everybody, in higher levels of math and science deals with this concept right here. That capital C in that formula is circumference of a circle. The distance all the way around the outside of any circle is given by this formula right here, 2 times pi times the radius. But as we said a while ago, radians work really well when we're talking about a unit circle. And our definition of the unit circle, everybody, back in 13.2, is that the radius is equal to 1. So if we were to replace this r right here with a radius value of 1, we'll check this out. Circumference then is 2 times pi times a radius of 1, and that just becomes 2 pi. So if you're on a unit circle with a radius of 1, the circumference of this circle, the distance all the way around the outside, is equal to 2 pi units. Now, a circumference is a distance. So that circumference might be 2 pi feet, it might be 2 pi meters, it could be 2 pi inches, it could be a 2 pi of a lot of different things. But the distance then of 2 pi around the outside corresponds then with the angle measure going around with it as well. So what that means is, and maybe we'll see this illustrated a little bit better later on, there's a 1-to-1 ratio then, everybody, between arc length and the measure of the corresponding angle. So again, not to dwell on this, but if I were just going to tell you guys, okay, you're on a unit circle right here, and this arc right over here, let me focus with this one right here, and that arc has a certain length, okay, the distance along that arc right over here, well, that distance then would be equal to this angle right here, an angle which we usually call theta. And I don't want to get into the actual radian angle measures just yet, but then this number and then this number, we usually call arc length S, would actually be the exact same thing. Okay, so that's kind of the purpose of radians. I don't know that we're going to see it just yet, but maybe by the end of this section, you guys will start to understand what they're good for. Okay, let's talk about what's going on right here. Radian measures of some common angles. I probably should have included the word common right there, guys, and I would stress right here that you memorize these as soon, as soon as possible. If you were to ask Algebra 2 students from previous years, how'd you do with trig and radians, they'll tell you they didn't like it. And if you ask them what went wrong or what would you have done different, they will probably tell you, I should have memorized all this stuff earlier on. Okay, so let's run through a few common things. Looks like we've got 6 of them right here. So, starting right here, a full circle in degrees, everybody, is 360. Hopefully everybody remembers that. And as we wrote down on the previous slide, a complete circle then is 2 pi for the number of radians. Kind of just weird to get used to, but this is the main definition right here for the connection between degrees and radians that we need to have memorized. After that, everything works pretty simply then. A half of a circle is 180 degrees, which makes total sense because 180 is half of 360. Now if we do the same things in radians, what is half of 2 pi? That is going to be just pi. Okay, so we're just dividing by 2 right there. Now, so we did half circle. Let's divide by 2 yet again, guys, a quarter circle. 180 divided by 2 gets you 90 degrees for a quarter of a circle. And if you take this pi right here and divide that by 2, now we start getting into fractional radians, guys. Pi divided by 2 is the radian equivalent of 90 degrees. Now from here it gets just a little bit more complicated, and I didn't have cool names for this. 1/6 of a circle. It's kind of difficult to think about how to get from 90 to 60. You're really, dividing by, 3/2 or multiplying by 2/3. But it's probably easier to think about the way I wrote this, 1/6 of a circle. So to get from a full circle to 1/6, you're going to divide that by 6. 360 divided by 6 gets you 60 degrees. And if we did that same trick right here, we would take 2 pi, let me jot this down at the bottom, for a full circle, and divide that by 6, and then we'll just simplify that fraction by dividing out a 2, and we'll get pi over 3. So a 60-degree angle, this is one we ought to know pretty soon, is pi over 3. Okay, how can we get to the next spot right here, guys? Let me get rid of some of those arrows because that's going to be confusing now. I think for 1/8 of a circle right here, it's not too hard to get from here to here. From 90 to 45, we just divide by 2. Then let's do the same thing from pi over 2 to this amount. We'll take pi over 2, cut that in half, and get pi over 4. So that's another equivalent that we ought to know. 1/8 of a circle, or a 45-degree angle, that's pi over 4 radians. And then I tell you what, let me just slide these arrows down right here, guys. To get from 60 degrees to 30, we just cut in half. So I'll do the same thing right here. Take pi over 3 and cut that in half. And that is going to give us pi over 6. Now everybody, these are 6 very common radian measures that are out there. These are not the only ones you're ever going to see, not by any stretch at all, but these are definitely the most common ones. And in what you guys are going to be asked to do by hand here with radians in a little while, if you can get these 6 equivalencies down right here, that 360 degrees is 2 pi radians, and 60 degrees is pi over 3 radians, and 45 degrees is pi over 4, and so on, you're going to be in pretty good shape. So let's go back to this diagram right over here, which we saw in 13.2. So this is my little AutoCAD version, guys, of the unit circle. And in 13.2, when we took notes on this, we did a whole lot of labeling. At all of those 16 points along the way, we're going to do pretty much the same thing right now, but we're going to do it in radians. So what I would really suggest you guys do, if you have this sheet here and you labeled it, I believe I made a handout to give you guys, and you labeled everything in degrees, I'd like you to grab the exact same handout, and on the exact same diagram, I'd like you to also label it in radians at the same points. We're going to walk through this together. It would be cool if you guys had a different color pen or pencil that you could switch to so that you can kind of keep things straight. So in degrees, let me go very quickly around the horn here, guys. This is where we started with a 0-degree angle, and then we had 30, we had 45, we had 60 degrees, 90 degrees right up here at 12 o'clock. This was 120 degrees. This was 135 and a 150 right there. We had 180 180 degrees right over here pointing straight west. Then we had 210 degrees, 225 degrees. This guy down here, I believe, was 240, and that got us to 270 pointing straight down here. Then we had 300, 315 at that next one, and 310. No, that's not right. 360 minus 30 would be 330 degrees for that angle right there. And that's what I like to call the Sweet 16, everybody. Those are the 16 angles going around the unit circle where special right triangles are formed. What do I mean? If I were to just pick one of them, like this 135 degree angle, if I were to draw the radius, which always goes back to the origin, and then an altitude, which always goes straight down to the x-axis, you form a triangle right here with a 45 degree reference angle. So this is a 45, 45, 90 triangle. So that's why these 16 angles are special. Furthermore, let me switch colors on you here, guys. I'll erase all this in just a second, but I could have focused on 300 degrees right over here. And if I drew my radius there and my altitude always to the x-axis right there, I have a 60 degree reference angle right here. So there's a 30, 60, 90. Okay, so that's why these 16 angles are special. They form special right triangles or quadrantal angles when you graph them. Okay, guys, on to it now. What we're going to start doing is taking these same 16 angles that are labeled in red and start labeling them in blue in radian equivalencies. Now, we start in the exact same position. So right over here to the right, guys, our initial position or our initial ray was 0 degrees. Well, guess what? That is also 0 radians. Now, unlike degrees, there's no cool symbol that you put on radians right there. So I guess technically I could just write an RAD for radians right there. But the thing about it is radians usually have a pi in there, but not always. Okay, what do I want to do, guys? I want to start breaking some things down right here. And what I'm going to do is go in a relatively small amount. I'm going to go back to that table we just did on the previous slide, and we're going to talk about the smallest increment here that we listed, 1/12 of a circle. 30 degrees is equal to pi over 6 radians. I'm going to write that up here in the corner. 30 degrees is equal to pi over 6. Well, that tells me one thing very quick and easily, guys. This angle right here, which is 30 degrees, that is equal to pi over 6 for its number of radians. But what I want to teach you guys to do right now is to kind of extend that idea and start jumping around the circle in a certain increment. And that increment here is going to be 30 degrees or pi over 6 radians. So starting at 0, when you go 30 degrees, you get to right here. When you go another 30 degrees, that gets you here. Hopefully that makes sense. 30 plus another 30 gets you to 60. But if we do the same trick with radians, pi over 6 plus another pi over 6 is going to get you to 2 pi over 6. But of course, we would simplify that fraction if we could and get it as pi over 3. Now that one should make sense because of this line that we wrote right here. 60 degrees is equivalent to pi over 3. And sure enough, 60 degrees gets us pi over 3 radians right there. Now, that concept, though, this 2 pi over 6 in the middle is temporary. I'm going to erase that. But that's kind of the way we're going to keep jumping around the circle. This was 2 pi over 6. Let's go another 30 degrees. That'll get us right here, which is 3 pi over 6. But of course, 3 over 6 simplifies to 1/2. So this then is going to become just pi over 2. 3 over 6 simplifies to pi over 2. Now that was 3 pi over 6. Let's keep going. Right here, 4 pi over 6, and that simplifies to 2 pi over 3. Right here, that would be 5 pi over 6. That one doesn't simplify. That one has to stay 5 pi over 6. Right over here, one more jump would get us to 6 pi over 6. Now write it down if you don't already know what's going to happen. 6 pi over 6, the 6's cancel, leaving you with just plain pi. And that, everybody, is what we said right here. Half of a circle, or 180 degrees, is equal to pi radians. So I'm going to clean this up a little bit. I'm going to get rid of that junk. I'm going to get rid of this. And I'm going to maybe slide this guy. Oh, no, 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 not you. I was going to slide this. No, doggone it. All right, that didn't work either. Well, I wanted to move this guy over here, so we'll just put equals pi over 3, and then we'll just erase that. That's kind of redundant. Let's keep going around the circle, guys. We were right here at 6 pi over 6. So this guy right here is going to be 7 pi over 6. That's the equivalent of 210 degrees. Another 30 degrees gets us right here. That would be 8 pi over 6, but the 8 over 6 simplifies to 4 pi over 3. That's an ugly 3. Keep going. This one here would have been 9 pi over 6, and the 9 over 6 simplifies to 3 pi over 2. All right, just 2 more here, guys. Another 30 degrees would have gotten us to 10 pi over 6, which simplifies to 5 pi over 3. And then the last one we have to label right here, again, this previous angle was 10 pi over 6. One more becomes 11 pi over 6, and that one doesn't simplify. And I guess if we were going to go just one more, we'd be right back here where we started, guys, which would be 12 pi over 6, and 12 over 6 just divides evenly to 2. So 0 radians is the same as 2 pi, just like 0 degrees was the same as 360 degrees. Those would be coterminal angles. Okay, moving right along here, guys, I've labeled, I think that's 12 out of the 16 angles now in terms of radians. Let me switch to green real quick. The ones that I haven't labeled, you guys will notice, are the 45s. So let's go back to that table right here, and let's take a look at this second to last line here. A 45-degree angle is equivalent to pi over 4 radians. So right here, 45 degrees is pi divided by 4. Now, if I were to keep going around the circle now in 45-degree jumps, this is 1 pi over 4. Right up here then, guys, would be 2 pi over 4. But of course, 2 pi over 4 simplifies to pi over 2, which we already knew right there. No need to label it again. But let's remember that this angle temporarily was 2 pi over 4. That's important because this angle right here now is going to be 3 pi over 4. And I'm just adding 1 to the numerator each time. This angle right here would be 4 pi over 4, but the 4's cancel and it gets you just the pi. Got it. This guy right over here at 225 degrees, that would be 5 pi over 4. Straight down would be 6 pi over 4, and that simplifies to 3 pi over 2. 6 pi over 4 plus 1 more here would be 7 pi over 4, and 1 more for good measure would get us to 8 pi over 4, and the 8 over 4 would again simplify to 2 pi. So there you have it, guys. That's all 16 special angles on the unit circle here, labeled both in terms of degrees and in terms of radians as well. Now, am I expecting that you guys are going to have all of these memorized? Eventually, yes, but what's more important to me is that you guys understand the process of jumping around the circle here in a certain increment or a certain size and being able to figure these angles out. So I wouldn't really say it's a memorization process, but it's more important that you understand how we got those angles, and hopefully then you would be able to derive those on your own. All right, so I definitely want you guys familiar with it. I want you working on memorizing it, but maybe we don't need to say that it needs to be completely memorized. Okay, what's one of the big things we're going to do? 2 formulas for us here, guys, for angle conversions. The first formula right here is the formula, and I guess I could have labeled this right here, but I'm hoping you can tell from the formula here, we're starting off in degrees and we're ending here in radians. So the formula for going from degrees to radians is to take your degree measure and multiply it by pi over 180. And thinking about units right here, the degrees on the top and the degrees on the bottom would cancel each other out and just leave you with radians. But what I'm really hoping you guys notice is that this fraction right here is what we call a unit multiplier. That means that the numerator and the denominator have the exact same value. The numerator is pi radians, and the denominator is 180 degrees. And I don't know if it's sunk in for you guys yet, but right here, there we go, this line, 180 degrees is equal to pi radians. So, what you're really doing is you're taking your degree measure and multiplying it by 1, which doesn't change the size of the angle. That's the whole point here, guys. All we're doing is we're converting the units then from degrees into radians, but we're not changing the value of the number. And that's a key concept that you guys are going to need to know if you're going to study chemistry or physics, because you do a whole lot of unit conversions right there. Let me go back to where I was here. You do a whole lot of unit conversions in those two subjects. So that's the formula for how to convert from degrees to radians. And then, going in the opposite direction, if you ever need to go, which you will sometime, from radians to degrees, we simply, oh, that moved on me, we simply multiply by the reciprocal of that unit multiplier, 180 degrees divided by pi radians. And this time, radians on top times radians on bottom will cancel each other out and just leave you with degrees, and that's where that unit comes from. Okay, so these are two formulas that we do need to have memorized. We're going to practice these right now, guys, but frankly, this is not a real difficult concept, and I expect you guys to do very well with this. So, my degree sign jumped on me right there. Okay, let's do two problems here together. The first one, 240 degrees, we're going to turn it into radians. So I'm going to start by writing 240 degrees, and we multiply that by a fraction. Now, since I want degrees to go away, that means I need to put degrees on the bottom, in the denominator of this fraction. So what we had there was that a half circle, 180 degrees, is equivalent to pi radians. Now, by the way, you certainly could, if you wanted to, realize that, okay, wait a minute, instead of that, we could have done 2 pi radians, which was equal to 360 degrees. That'll work perfectly fine too, but that's just got a 2 and a 360 in it that you're going to have to simplify anyway in just a minute. The pi over 180 is already a simplified version of that fraction. So what happens now here, guys? What I would do if I were you guys is I would grab my calculator and I'd probably put in the old stacked fraction right here, guys, of this over this, and I'd probably put in 240 over 180, and it'll simplify that fraction for you. What I'm hoping you guys notice is that 60 is the greatest common factor of those two numbers. And 240 divided by 180, we can pull a 60 out of both of those and end up with a 4 over 3, and the pi can either go out at the end of this whole thing, or you could put the pi in the numerator. 4 pi over 3, both of those are perfectly fine. So either one of those is the correct answer right here. I guess I usually put my pi in my numerator right there. Didn't really realize I did that, but yeah, that seems right. Now this one's pretty straightforward, guys, because if we go back to the wheel right here, this is already one of the special angles that we knew right there. 240 degrees down in the third quadrant right here is equivalent to 4 pi over 3 radians. So that's one we could have cheated on right there just by looking at the unit circle in our notes. But I want to remind everybody, those sweet 16, guys, they're not the only 16 angles that are out there. Let's take a look at a weird one like 162. So if I took 162 degrees and multiplied that now by pi radians divided by 180 degrees, what's going to happen this time? Well, I would go to my fraction and I would do 162 over 180, and this time, if I'm not mistaken, it's an 18 that divides out from both of those. That's pretty easy to see if you know what you're doing. In the denominator, 180 divided by 18 is just going to be 10, and since 162 is 18 less than 180, that would just be a 9 right there. I would expect you guys to verify this right here and not just trust me, but that's going to get us a 9/10, and I'll put the pi in the numerator then, and that's my answer then, guys. 9 pi over 10 radians is equal to 162 degrees. That is not one that we can confirm just by looking at the chart right here, because 162 degrees or 9 pi over 10 is not one of the sweet 16 angles there, but this one does pan out. Let's go the other direction, guys. Let's convert from radians now into degrees. I had to write that one by hand, sorry. So what are we going to do here? We're going to take our radian measure, which is 7 pi over 4, and we're going to multiply that now by 180 degrees. That's my numerator now, over pi radians, which is in the denominator. And what I see here is that a pi in the numerator times a fraction with a pi in the denominator, well, those pi's will just cancel out completely. So my answer isn't going to have any pi in it. That's nice. And now I take a look at the 4 and the 180, and I'm pretty sure that 180 divides evenly by 4. So 4 divided by 4 is 1, and 180 divided by 4. Guys, if you ever need to divide a big number by 4 in your head, cut it in half, and then cut it in half again. Half of 180 is 90. Half of that 90 then is 45. So all I'm left with here then, guys, is a 7 times 45 up in the numerator. And I'm sure you guys would use your calculator right here, but that's a 5 and a 3 and a 28. And that's going to get us 315 degrees now, everybody, for the equivalent of 7 pi over 4. And as I write that, now I feel kind of silly because I'm pretty sure, yep, right there, that was another one of the sweet 16 angles right there, because we ended up with pi over a nice number like 4. So 2 of those 3 examples that I gave you, I guess we could have cheated on and looked at it that way, but I wanted you guys to get some practice here. I believe that on most of your homework problems, they are not 16 of the 16 special angles, and you're going to end up with some kind of funky numbers right there. Okay. On to the concept now that really scares people at first, but if you did well with section 13.2, this really isn't any different. Finding sine and cosine and tangent of an angle if we're talking about radians now, guys. So let's take a look here. Theta is 2 pi over 3. Now, without going back and looking at our graph again, here's what I would want you guys to remember. The denominator right here is 3. So what I would need you guys to know here is that pi over 3 is equivalent to 60 degrees. We got that from our table. So we're going to start right here, everybody, at our initial position, just like always, at 0 radians. And we're going to go in 60-degree jumps around the circle, and we're going to make 2 of those 60-degree jumps. So one 60-degree jump would get us right here, which is pi over 3. Another 60 degrees would get us to this angle right over here, and that one is what we were looking for. That's going to be 2 pi over 3. We went 60 degrees for 1 pi over 3, and then we went another 60 degrees to get to 2 pi over 3. And now that we're here, everybody, this is the beauty of this diagram that I'm going to give you guys as much as I can. You plot a big fat dot right there at 2 pi over 3, and you draw your right triangle from that point. How? You always draw your radius going back to the origin there. Got it? And you always drop an altitude straight up or down from that point. In this case, it's down, always to the x-axis, guys. And then we just connect those, and there's your right triangle. And what I'm hoping we're getting the hang of here soon, everybody, is that this has to be, because it's one of the 16 special angles, a special right triangle. Your reference angle right here is 60 degrees. That means we're dealing with a 30-degree angle right here, and this is a 30, 60, 90 right triangle. And so, now that we know that, let's label our side lengths. Now, I want to remind everybody, we are dealing with a unit circle. And on the unit circle, your radius is always 1. So this piece right here has a length of 1. And I'll remind you guys, the radius in a unit circle is always positive, never negative. So it's always positive 1. Then, these numbers that I asked you guys to memorize from 13.2, a 30, 60, 90 triangle on the unit circle has a short leg of 1/2. But since this point right here, I'm talking about this point, guys, is to the left of the origin, this is actually a negative 1/2. Then, the long leg, the vertical piece, is going to have a length of the square root of 3 divided by 2. Now, since this point right here exists above the origin, this y-coordinate is going to be positive. So, With all that in mind, let me get rid of this here, guys, and let's write out the three things that we need to know. At this point, right over here, everybody, our x-coordinate, this amount right over here, is negative 1/2. Our y-coordinate, which is the vertical component right here, is positive √3/2, and our radius, this is kind of a trick question, is always positive 1. And now that we know the x-coordinate and the y-coordinate at this point right here, that's what we just found, and we know, of course, that the radius is 1, this should be relatively simple to find, for starters, the sine of the angle 2 pi over 3. The XYR definition that we learned about of sine back in 13.2 is that sine is y over r. But since r is 1, since we're on a unit circle, sine is just your y-coordinate right here, which is √3 divided by 2. Done. Cosine of 2 pi over 3. Okay, the definition we learned back in 13.2, if you're on a unit circle with a radius of 1, is that cosine is just your x-coordinate. Cosine of 2 pi over 3, negative 1/2. That one's done. And lastly, this is going to be the hard one, guys, tangent of 2 pi over 3. All right, tangent's a little tougher. The definition of tangent, whether you're on a regular circle or a unit circle, is y over x. So this one, then, is going to be a complex fraction, guys. Y here is the square root of 3 over 2, and your x-coordinate is a negative 1/2. So how do we divide a fraction by a fraction? We leave the first fraction alone, √3 over 2, and then multiply by the reciprocal of the denominator, which would be 2 over negative 1. The 2's, top and bottom, being multiplied, cancel each other out. And we're left with the square root of 3 over negative 1, which is simply negative square root of 3. So there's your answer for sine of 2 pi over 3, there's cosine of 2 pi over 3, and there's tangent of 2 pi over 3. Now, you're welcome to check that in your calculator, everybody, and unfortunately I don't have a TI-84 on my iPad here, so I can't show you that, but I'll warn you, if you're going to type this expression here into your calculator, you've got to make sure that your calculator is in radian mode. If it's not, it's going to give you the wrong answer here. Now, when you type that in, if you do that, sine of 2 pi over 3, you're going to get a messy decimal that I believe is 0.0866 blah, 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 blah. Well, then, if you were to type this expression into your calculator, it'll give you that exact same ugly, irrational decimal number again, and that'll be your way of knowing that you got that right. You would need the same trick here with tangent, but luckily cosine is a rational number. There your calculator would have just given you negative 0.5, and that one's a lot easier to see. All right, so I want to do 2 more of these with you guys, but I'm hoping you're starting to get the hang here of how to evaluate sine and cosine and tangent at the 16 special angles around the unit circle. Let's try it again here, everybody. So the next one I've got for you, a little bit tougher, is negative 9 pi over 4. So, first thing we have to do, locate that angle. So we always begin straight out to the right, pointing east. We're going negative this time, everybody, which means we are now going to proceed in the opposite direction from what we normally do. We're going to go clockwise. And how far are we going to go? Well, look at your denominator, which is 4. So we need to know, or remember, everybody, that, I'll do this in blue, that pi over 4, this is something I want you guys to have memorized soon, is 45 degrees. So we're going to go in 45-degree jumps or steps around the unit circle. And how many of those steps are we going to make? 9. I guess negative 9, because we're moving in the downward direction right here, opposite of what we normally do. So here we go, guys. Starting right here, this first jump right here is negative 1 pi over 4. 2, 3, negative 4 pi over 4, 5, 6, 7. Right back here where we started is negative 8 pi over 4, which is negative 2 pi. That makes sense. And one more step right there, guys, gets us to where we wanted to be. This guy right here, there we go. That angle there, theta, is negative 9 pi over 4. We took 45-degree jumps or steps around the circle. We did 9 of them, but we worked in the clockwise direction because this angle was negative. So all that other fun stuff that I did, I'm going to erase now so we don't confuse you guys. All right. And I would like to think that eventually, once we get the hang of it, you guys will be able to locate that angle very, very quickly. So here then is the terminal side of the angle. That also becomes the hypotenuse of the triangle I'm about to draw. And remember, guys, never, never, never do we draw an altitude over here to the y-axis. You will never see that. We always bring our altitude up or down, up in this case, to get to the x-axis. So there's your right triangle formed at theta equals negative 9 pi over 4. Your reference angle, I'm hoping you can tell this from this diagram, guys, is 45 degrees, which shouldn't surprise you, which means we're dealing with a 45, 45, 90 right triangle. So let's start labeling our sides. Now, with what you were asked to memorize in 13.2, in a 45, 45, 90, on the unit circle, the radius is always 1. And I'll say it again, it's always positive 1. The radius is never negative. But the side lengths then, everybody, are this ugly irrational number of the square root of 2 over 2. I should have said the length of the legs, root 2 over 2. The one that I just drew there, the x-coordinate, since we're going to the right of the origin, that one should stay positive. The other leg is also root 2 over 2, but since that one is going down from the origin, that is going to be a negative root 2 over 2. So I think at this point right here, we know what we need to know. Our x-coordinate is the square root of 2 over 2. Our y-coordinate is negative root 2 over 2, and our radius, again, is always 1. I didn't mention this earlier, guys, but we are here in the fourth quadrant, everybody. And in the fourth quadrant, your x-coordinates are always positive, check, and your y-coordinates are always negative. On that previous problem, we ended up in the second quadrant. And in the second quadrant, x is always negative, which this one was, y is always positive. That's a great thing to think about just to make sure you haven't made a little error in terms of the signs, S-I-G-N-S, of your values. Okay, now that you know x and y and r, figuring out sine and cosine and tangent should be pretty simple. The sine of negative 9 pi over 4 is equal to, you could do opposite leg over hypotenuse, you could do y over r, but since we're on a unit circle, which I know because r is 1, sine is just my y-coordinate right here, guys, which is negative square root of 2 over 2. That's as good as it's going to get. The cosine of negative 9 pi over 4. Again, cosine you could think of as adjacent leg over hypotenuse. You could think of it as x over r. But again, because we're on a unit circle with a radius of 1, cosine is just your x-coordinate here, which is positive root 2 over 2. As good as it gets. Now this one, tangent, was the difficult part on the previous problem, but I think you guys are going to like this here. The tangent of negative 9 pi over 4. Okay, our XYR definition of tangent, everybody, is y over x. So when I write that as a fraction, it looks pretty scary at first. My y-coordinate is negative root 2 over 2. My x-coordinate is positive root 2 over 2. And that looks kind of skunky until you realize we're just dividing one number by its opposite. Negative root 2 over 2 divided by positive root 2 over 2. Anything divided by itself is 1. Any number divided by its opposite is simply negative 1. And that's it, guys. That's the value of the sine of negative 9 pi over 4, the cosine of negative 9 pi over 4, and the tangent of negative 9 pi over 4 as well. Now, once more, you could verify this on your calculator, but you'd need to be in radian mode. And on these two answers here, this guy and this guy, you're probably going to get a decimal of 0.707. Actually, that first one would have been negative, but you can verify that one as well. But the tangent value should have come out perfectly for you since -1 is a rational number. Okay, so those are two angles. In the first example we did here, 2 pi over 3, we got a 30, 60, 90 triangle. In the second example we did, -9 pi over 4, we got a 45, 45, 90 triangle. And the only other thing I'm going to do with you, because we haven't done it yet, is an example like this where you're not going to get either a 30, 60, 90 or a 45, 45, 90. What else could it be? Let's play with this guy right here. Woo! Theta is equal to 35 pi. No fractions here at all. So what I'm going to remember now, guys, is that 1 complete pi right here is equal to 180 degrees. So if I start here at 0, pi radians gets me right over here. That's half a circle. And then if I keep going, another half circle gets me to 2 pi. I'm not there yet, so let's keep going. Yet another half circle, this angle here would also be 3 pi. And if I add one more, I also get 4 pi right over here. And now I think maybe I'm starting to see a pattern. Another half circle would get me to a 5 pi. This here would be a... Okay, I get it now. All the even coefficients for pi end up right over here. So something like 100 pi would be in that same spot. But pi with an odd coefficient is going to end up right over here. And that's what we're looking for here, guys. 35 pi. Okay, so that one is going to be pointed straight over to the left. So a little bit of exploration right there, but I'm not sitting there going around the unit circle 17.5 times. This angle right here, guys, is 35 pi. Now, what I would normally tell you guys to do once you've located your angle, your point on the circle, is draw the triangle. Okay, and usually I tell you to draw the radius and then an altitude to the x-axis. Well, I guess I'm going to tell you the same thing right now. Draw your radius, which always goes back to the origin. Got it? And your altitude to the x-axis. Well, that doesn't really exist because this point is on the x-axis already. It's not like when we were right here and you could draw an altitude coming down to the x-axis like that, and boom, you actually have a triangle then at 5 pi over 6. This one doesn't create a triangle because here's a phrase I used in 13.2 for you guys. This is what we call a quadrantal angle. Okay, it's one of the angles that's located either straight up at pi over 2, straight left at pi, straight down at 3 pi over 2, or straight right at 0 or 2 pi. And at those 4 quadrantal angles, you don't have a triangle, guys. All you have is a line segment. So if you're going to stubbornly cling to the idea of SOHCAHTOA, that concept here that sine is opposite over hypotenuse, it's going to work just fine for you on this problem, and it's going to work just fine for you on this problem, because on A and B, you have a triangle. But when you don't have a triangle, the concept of opposite leg, adjacent leg, and hypotenuse just doesn't make any sense. So this is where the X, Y, R definitions of sine, cosine, and tangent make a lot of sense. All right, guys, where are we? What is our X coordinate at this point right over here? Well, starting at 0, we've moved left. And remember, since this is a unit circle and our radius is 1, we just moved 1 unit to the left. This ordered pair has an X coordinate of -1. The y-coordinate tells you how far above or below the x-axis you are. Well, since this point is on the x-axis, that y-coordinate is going to be 0. And that tells us that y is 0 right there. And the radius, everybody, once more, I think this is about the 8th time I've said it here in this video, since we're on a unit circle, your radius is 1. And the radius is never negative. The radius is always +1. And guys, as soon as you write that point, as soon as you label its coordinates, and as soon as you come up with the values of x and y and r, everything else is pretty simple. The sine of 35 pi then, sine is y over r, but since r is 1, sine is just your y coordinate, 0. Cosine of 35 pi. Cosine is x over r, or because it's a unit circle, just x. Cosine there is negative 1. And then lastly, the tangent of 35 pi. Once again, tangent is y divided by x. That's going to be 0 divided by negative 1, which simplifies to 0. And there it is, guys. That's the value of sine of 35 pi, cosine of 35 pi, and tangent of 35 pi. I kind of hope that after those last three examples, guys, I'm making this look easy here, because that's the process I want you guys to get through. So you're never going to be asked to memorize the sine and the cosine and the tangent of every angle that's out there, but it's a process that you guys have to learn, whereby you draw the angle, locate the coordinates there, figure out all of the values of x, y, and r, and then just apply those values to your definitions for sine and cosine and tangent. All right, there's a little bit more in this section, but I'm going to save that for a future video if we're going to talk about arc length and area of a sector, but I think that's plenty for right now. All right, guys, get started on that 13.3 homework. Good luck, guys.